And now I invite our colleagues from Taiwan, Thi-Na, to start presentation.
My name is Thi-Na Ta. I'm from National Formosa University in Taiwan. And today I'm going to talk about our research on characteristics of surface damage of ZDDP containing lubricating oil. First, I'll talk about the motivation why we have been doing this research. As you know, the tribological degradation of the surface of machine parts is usually caused by excessive wear, scuffing, and pitting. If one of the reasons cannot not improve, the lifetime of machine parts will be decreased. So some scholars they propose running in process to prevent the premature failure. With this process, it can remove the surface asperity by wear or plastic deformation under controlled operating conditions. Another way to limit wear is adding the additive into lubricant. And one of the most common used additive is ZDDP. However, the ZDDP have different reactions under various operations, so the investigate on the characteristic of ZDDP still be one important topic in tribology. So the main goal of our research is to study the effects of the running-in process and different operating conditions on tribological performance at different weight percentages of ZDDP. Here you can see our experimental procedure. First, we perform experiment on 4-ball weight test. From this machine, we can measure the friction force, the oil temperature. After experiments, we use optical microscope to measure the wet scar diameters and see the wet scar surface morphology. And we can analyze the pitting. Next, we use 3D optical microscope to calculate the wear volume and measure the wear surface roughness. In the last step, we use a Palmas particle counter to count the particle inside the oil after experiments. The material we used in our experiment was the standard 51200 steel ball, and the test lubricant was a circulation oil R100, which has 100.2 centistock kinematic viscosity at 40 degrees Celsius and 97 viscosity index. As I said before, in my experiment, I used ZDDP additive with 4 different weight percentages: 0.25, 0.5, 1, and 1.5. You can see here the ZDDP we used includes 7.6% of zinc, 6.6% of phosphorus, and 13.8% of sulfur. Here is the 4-ball wear test machine. A top ball was locked into the main shaft of the machine and to rotate and rubs against 3 fixed balls. In order to consider the effect of running process, our experiment was performed into 2 steps. In the first step, we call it running process. You can see here is some operating condition like rotating speed was 600 RPM and the constant load at 40 kgf, and the oil temperature was set at 75 degrees Celsius, and the takt time was 1 hour. In the second step, we change the rotating speed to 900 RPM, and we apply a step load from 20 to 110 kgf, and the oil temperature also set at 75 degrees Celsius. In this case of no running process, the first step was omitted. You can see here in these two figures, it shows the coefficient of friction and oil temperature during running process. What you can see here is that the coefficient of friction when we add ZDDP was higher compared to the original oil, and the oil temperature was stabilized after 20 minutes of experiments. After running process, we measure the waistguard diameter on 3 fixed balls, and we take the mean value of this waistguard. And you can see here when ZDDP additive was added into the test, the weight were reduced about 35%. These images show you the waistguard surface morphologies after running process. You can see the difference between the test with the ZDDP additive and the test with the original oil. Is here some blue reason appear on the weight checks, and some previous researchers they said that this is the tribal film formed by ZDDP to protect the surface. Here is the coefficient of friction when we apply the step load with the percent of running process and without running process. In the first figure, you can see the test with the ZDDP additive, so higher coefficient of friction than the test with the original oil 100. And when 1% with percentage of ZDDP were added into the test, the coefficient of friction smaller compared to other with percentage of ZDDP. In the case of no running process, the coefficient of friction increased as we increase the load in the first two steps until 50 kgf, and then the coefficient of friction decreased as we continue increase the load until 110 kgf. You can see here the scuffing failure phenomenon was occurred for the test with the base oil. After the test with step load, we also measure the waistguard diameter on the 3 stationary balls, and we take the average value for the waistguard diameter. And in case of running process, the waistguard diameter when we add 0.5 with percentage of ZDDP has smaller than the other tests with ZDDP. But in case of no running process, 0.25 with percentage of ZDDP has smaller waistguard diameter than other amounts of additive. also see the waste gas surface morphologies in case of branding process. And you can see here the blue region is smaller than the test after running process. It's because of high rotating speed and high load may block away the tribal film formed by ZDDP. In case of no running process, you can see here for the test with the original lubricant, something was occurs. So here the balls suffer the severe damage. From the Wesker morphologies, we perform the pitting analysis. The percentage of pitting area on the surface of the steel ball, as indicated by the red dot in this figure, was calculated by using an optical microscope and image analysis software. This pitting analysis result for running case and non-running cases. What we can observe here is that the percentage of pitting area will reduce about 45% when the ZDDP additive included in the test. And for the test with running process, adding 0.5 with percentage of ZDDP at the pitting area smaller than the other cases. For no-running case, we can see the 0.25 weight percentage tend to a lower value compared to other cases of ZDDP. From after experiments, we count the particle inside the oil, and you can see here is the number of particles in range of 0.5 to 20 micrometer in case of blending process and without blending process. And here, when the ZDDP was added to the test, the total number of particles was significantly decreased compared to the test with the base oil. And the quantities of particles in case of no running is smaller than that of running cases. From wear scar diameter and wear particle, we calculate the wear volume and volume of wear particles. The results show that wear volume calculated from wear scar were higher than that from wear particle, but the trend of them are similar. And from these two figures, we can also see that in case of running process, adding 0.5 weight percentage of ZDDP present a lowest wear volume. And for no running process, 0.25 had a better reduction on wear volume. From our experiment results, we try to find the relationship between the wear particles and pitting area. And we can see that the smaller the total number of particles, the smaller pitting area can be obtained. Here, the relationship between the number of wear particles in case the no running process have a similar chance and the case of running process. So we predict that the wave particle and fitting have a proportional relationship. From wave scale diameter, the wave volume and fitting area in case of running process, we obtain that addition of 0.5 representative of ZDDP to the lubricant can reduce wear and fitting better than that of the other percentage of ZDDP. And in case of no running process, adding 0.25 representative of ZDDP can decrease the surface damage as it can reduce the wear and fitting better than the other cases. Now, just to summarize, let's quickly look on our achievement in our research. First, for the test with lubricant R100, the sculpting was prevented with a present running process. And when the ZDDP were added to the test, sculpting did not occur for all the tests. It's proved that running in process and ZDDP can improve the tribological performance. When we change the weight percentage of ZDDP additive, the coefficient of friction in case of running in process was higher than that in case of no running process, but wear was reduced for all the tests. In the presence of wear in process, 0.5 representative of ZDDP test could reduce wear and fitting better than other cases. But without wear in process, 0.25 representative of ZDDP can present better tribological performance than the other representatives. And the percentage of fitting area will reduce about 45% when the ZDDP additive was added to the test. And our experiment results show that the wave particles and fitting have a proportional relationship. Okay, I just finished my presentation. Thank you for listening.
Thank you very much for your very interesting talk.